Good morning to everyone. My name is Valerio Setti, and the topic of my presentation and PhD is the hollow core fibers for Terahertz application. My tutor is Professor Luca Vincetti. And of course, the desired feature for a generic waveguide are low loss propagation, broadband transmission bandwidths, and of course it must also be flexible just to allow for a dynamic Terahertz setup to be taken into account. As you may know, classical waveguides have some problems in the Terahertz frequencies because, for example, metals have low conductivity and most of the time they are also not flexible. And whereas dielectric waveguides suffer from high absorption of the dielectric materials at Terahertz frequencies. Here I show you the typical absorption spectrum of two kinds of polymers, PMMA, polymethyl methacrylate one, the red curve, is very used in the infrared spectral region, but as you can see at 1 Terahertz, it has an absorption rate of 80 dB per centimeter. Topaz or Xeonex, which are two of the most transparent polymers used nowadays, and for Terahertz frequencies, still have 1 dB per centimeter, making it quite complex to have long distance propagation with these solid core fibers. Well, air is one of the most transparent materials. Here you can see a typical absorption spectrum measured with different kinds of atmospheres. And yeah, you can see that below 1 Terahertz, the absorption is below 10 to the minus 3 dB per centimeters. And even though there are some peaks due to water vapor, which is present in air, in the air atmosphere. However, this very low absorption suggests a new way of designing optical waveguides. And starting from, for example, porous fibers, microstructure suspended core fibers, and then finally hollow core fibers. That are what we are going to talk today. And as you, well, different structures have been proposed in the literature, starting from the most simple one, the standalone dielectric tube. Well, it's very simple, but it suffers in general from high propagation loss and multimodality. But also Bragg fibers, which has lower propagation loss, but in general not wide transmission bandwidth. And then finally, that are those we are going to consider today, microstructure fibers. Well, they allow a reducing of the confinement loss with respect to the other fibers, and they also have multi-octave guidance. And well, different structures have been proposed in the literature, as you can see from here. These are known as Kagome fibers, the top one, and these one are two pictures for tube lattice fibers. Okay, this is a short summary of the activity I've done during the first 2 years. Well, due to lack of time, we're going to simply consider the waveguiding mechanism for this kind of optical fibers. The structure is very simple. The cladding is formed by a triangular arrangement of hollow dielectric tubes. Each tube has its own physical and geometrical dimension, of course, and the core is formed by the removal of the 7 innermost tubes. The advantage of this fiber is that they have wider transmission bandwidth than photonic bandgap fiber, and since there's no photonic bandgap, actually, they allow only one turn of ring of tubes to be taken into account around the core, and this gives a more compact waveguide with respect to photonic bandgap fibers. And another important aspect is that they can be assembled manually, which is, of course, very interesting. Okay, as I told you at the beginning, different structures have been proposed. And as you can see from the picture here, they are actually very similar. And what changes is the shape of the tubes that are used in the cladding, circular or polygonal, and in particular hexagonal. And even though they are very similar, they have very different performances in propagation loss. And in particular, if you consider the Kagome fiber with the hexagons in the cladding, you have much higher propagation loss than the circular case. So let's take a look how does this waveguiding mechanism works. So, well, here's a schematic representation of this confinement mechanism. The core mode is bounded inside the hollow core region by multiple reflection on the cladding interface. However, since there's no photonic bandgap for this fiber, at each bounce, part of the radiation is lost outside the waveguide, so we call this leakage loss. And Well, but since the cladding is quite complex, it's rather simple to consider a model analysis of the waveguide instead of a bouncing mechanism. So for this structure, we can say that there are two different classes of modes, the core ones confined in the central part of the fiber and the cladding ones. And cladding ones can be divided in two different classes, the whole ones, like these ones, or the dielectric ones. And yeah, the propagation loss, as is reported here, as an example, and as you can see, it alternates high and low loss propagation regions. In particular, high loss regions are due to the coupling between the core mode and the dielectric modes. Whereas where there's no coupling between these two classes of modes, there we have low propagation regions. And yeah, okay, the results have been reported in this picture, considering a normalized frequency, and according to this normalization, the high loss region are placed at integer values of this normalized frequency. Okay, the previous model that has been proposed in the literature were just for the Kagome fibers, and it tends to model the cladding as an intersection of slab waveguides. Yeah, it's very simple as a model, but and it is able to predict the spectral position of this high loss region. But at the same time, the main lack is that it cannot predict the spectral width of this high loss region. So our idea is that in both Kagome and tube lattice fiber, the cladding can be composed as an arrangement of tubes. Of course, what changes between the two structures is the shape of the tube. So our idea is that we can start from considering the standalone tube itself and then move to the microstructure cladding by using the coupled mode theory. Of course, what it is interesting in our solution is that the circular tube can be investigated analytically. So carrying out calculation, we have considered what happened when we consider the modes of the standalone tube by changing the rho parameter, which represents the ratio between the internal and external radius of the standalone tube. Well, what happened is that as long as we move from 1 toward 0 rho values, which means that we are dealing with thicker tubes, then we have that the modes of the tube spread over a wider range. And for each transmission window, here, here, and here, you have that there is a critical rho values at which these curves cross each other. So let's take a look at what happened when we consider this model to our microstructure fiber. And here you can see a comparison between three similar kind of structure with different rho values, and in particular 0.75, 65, and 0.4 finally. And as predicted by our model, as long as the rho value is reduced, we have that the transmission window tend to first decrease and then finally disappear, which justify our model. So in conclusion, we can say that in order to have low loss propagation and broadband transmission, it is important to work with rho values which are as close as possible to 1, which mean very thin structures. Okay, now moving on, let's consider what happened when we change the shape of the cladding tubes. In particular, let's see what happened when we change this circular shape to, in general, a polygonal shape with n sides. Here you can see a comparison. The red dots represent the circular case, and as you can see, it's the best, it gives the best performance over the entire spectrum. Whereas the polygonal ones have some additional resonances, additional increased losses at the center of the transmission window. And in particular, with these vertical lines highlight the fact that the higher the number of the side, the higher the frequency at which these extra losses appear. So this can be taken into account considering the fact that the polygonal shape can be seen as a perturbation of the circular one with this kind of perturbation function. Well, if we take this in our coupling model shown before, we can state that this kind of perturbation allows in the polygonal case to have resonances that in the circular case they were inhibited. So, carrying out calculations and considering the fact that this perturbation is a periodic function along the azimuthal direction, it is possible to determine the spectral position and spectral width of this increased loss region given by this formula here, in which A and B are, well, parameters that depends on the geometrical characteristic of the circular tube taking as a reference, and M is a generic integer value. So here we can apply this model to a comparison between the circular case and a 12-sided polygonal tube lattice fiber. Rectangles here represent the application of this formula with different M values. And as you can see, they're perfectly able to predict the position of this extra resonance. So what matters most, actually, is the position of the first resonance, since it's the first one that appears in the frequency. Well, it's not difficult to prove that the first resonance is found at this normalized frequency. And since A and B are fixed for a waveguide, we can conclude that in order to shift this extra resonance toward higher frequency or out of the frequency range of interest, it is essential to increase the number of the sides of the, in the polygons. So now we can understand the reason for difference among, between circular tube lattice fiber and Kagome fibers. Well, Kagome fibers having n equal to 6, well, it's an hexagon, it represents the worst case, since, as shown here by our model, it's full of extra resonance over the entire spectrum, whereas the circular case shifts this extra resonance to an infinite frequency, making it the best case that we can achieve. So, this is a short summary of the activity that I've done during this last year of PhD. Well, due to lack of time, I'm simply going to consider the manufacturing and characterization of a real fiber. And this has been done at the Institute of Photonic and Optical Science at the University of Sydney. And, well, before moving on, we can say that we have changed the geometry from the previous triangular lattice model to the circular one. Indeed, our fibers, in general, all core fibers have a core radius which is much bigger than the working wavelength. This means that there are more than one mode, in general, multitude of modes that can propagate inside the hollow core. Well, the problem, a possible solution to reduce the effect of these high-order modes is to increase their losses with respect to the fundamental one. Well, due to geometrical constraint, actually, it is very hard to accomplish this point in the triangular lattice shown before. So we decided to change this geometry to the circular case. Well, that's due also to the fact that the confinement mechanism does not rely on the particular arrangement of the tubes, but simply on the spectral properties of the tube itself. Well, we found also that the optimum number of tubes around the core, in order to increase the differential loss, it's 8. And as you can see from this graph, in which we plotted the differential loss with respect to the fundamental loss, moving from the triangular lattice structure to the octagonal one, we have an upshift of the curve, which means that at the same level of loss for the fundamental mode, we are increasing the differential loss. That is what we were looking for. So, this is a microscope picture of the circular tube lattice fiber that I've manufactured. I started from polymethyl methacrylate tubes, and these are the dimensions of the initial preform. Polymethyl PMMA, it's a commercial available polymer, and it's also very cheap, making the final fiber extremely cheap. And then, okay, these are the final dimensions for the jacket and the cladding tubes, giving a core size of 1.62 millimeters. Another important feature of this structure is that it's a self-sustained structure, so no gluing or further drawing steps were required to keep the tubes in place. And another improvement for our waveguide was that instead of using dielectric cladding over the entire length of the fiber, we decided, well, that gives some problem connected to the fact that this jacket, it's very robust, so it's not much flexible, but we want a flexible waveguide. So we decided to cut it into pieces of in 5 millimeters in length and put them 10 centimeters apart from one to the other. This allowed us to keep the tubes in place. but without affecting the flexibility of the fiber. The remaining part of the jacket was substituted with a heat shrink tube. This has been added manually, and the interesting part is that the heat shrink tube has a shrinking temperature which is much lower to the transition temperature of the PMMA, so we are not changing or perturbing the shape of the cladding tubes. And this, as you can see from this picture, allows us to obtain also a very flexible waveguide. Yeah, the characterization has been performed through a Terahertz time domain spectroscopy system, which is represented schematically here. And the interesting part of this setup is that you have pulses that are produced by our photoconductive antenna here, and they pass through the fiber, and they're being then recollected and refocused at the photoconductive antenna. But the fact that we are dealing with pulses, we are working intrinsically with one broadband feature, so we can determine both amplitude and phase information that allows us to calculate both dispersion, which is effective index for the fundamental core mode, and the propagation loss. So these are the formula that I've used to compute the effective index of the fundamental core mode and the absorption loss. In the first case, I have compared the free space propagating pulse with the one that's propagating inside the hollow core fiber. Whereas in the second case, I've compared the pulses propagating inside fibers of different lengths, and this allowed me to avoid coupling efficiency calculation, like in the very classic cutback measurement for infrared or other kind of classical waveguides. Here you can see a comparison between the numerical result represented with a dashed black line and the experimental one. And as you can see, there's a very good agreement for both the dispersion and the propagation loss. But talking about raw performances, here we can compare the propagation loss shown before with the bulk PMMA absorption reported with a red line. And as you can see, for both the first and the second transmission window, we have a strong improvement with respect to for the propagation loss with respect to the bulk material, giving us a propagation loss as low as 0.3 and 0.16 dB per centimeters. And we have then numerically consider also other kind of the same waveguide but with other kinds of polymers used to manufacture the cladding tubes. And we have shown that if Xeon XOR topaz, for example, are taken into account, we can reduce the propagation loss even further of 1 and 2 order of magnitude for the first and second transmission window respectively, allowing an extremely loss propagation for this kind of waveguide. The bending has been characterized using the same setup, but in this case, the receiver has been moved in order to form a 90-degree angle with the transmitter as shown on this picture. And then to do the bending measurement, we tilted the end part of the fiber, and then through a couple of mirrors, we redirected it through to the receiver. Well, it was not that easy to get a good alignment for the Terahertz radiation since it's not visible. But however, here you can see a comparison between the numerical and experimental normalized transmission for our waveguide. And as you can see, there are two main effects that are connected to the bending. The first one, highlighted with this red region, is a slight reduction of the transmission bandwidth for both the transmission window, and also a reduction, an increase of the propagation loss in the middle of both transmission windows. Well, the agreement with the numerical results is still good. However, we found some discrepancy for the 10 centimeter bending case, and we think that, as you can see from this picture, this might be due that for such a tight bending, the input and output part of the fiber are quite, strongly perturbed, and this may alter the input and output coupling efficiency of the fiber, thus perturbing the results. So, in conclusion, we can say that during my PhD activity, I have analyzed the waveguiding mechanism in tube lattice fiber. And everything started with the consideration that the cladding can be studied starting from the single tube that constitute its shape. And in particular, from this model, we were able to investigate the correlation between the geometrical feature and the spectral performance, but also the condition for the existence of transmission window, effectively single mode propagation, and then finally, also the effect of the shape on the propagation loss. At the same time, we have also considered perturbation of the ideal structure, such as an undesired or desired effects for an elliptical core perturbation, and also bending effects have been characterized as well. Finally, during this last year, I was able to design, manufacture, and characterize a real fiber, showing that these hollow core waveguides allow strong reduction of the propagation loss with respect to the bulk material, and they represent, they also have a very low sensitivity for the bending, for bending radius major than 20 centimeter. And this feature make them very interesting as waveguide to be used in dynamic Terahertz setup for both imaging or sensing. Well, before concluding, here's a list of my publication that I've done during this year. And okay, this concludes the presentation. That's all. Thank you for your attention, and I'm available for questions.
Thank you very much for the presentation. Are there any questions? No. Okay, thank you again. So now, in 10 minutes, we have the buffet outside the door here in the corridor. And then we will start again at 2:15 in the afternoon. Okay. Thank you very much for attending.